Okay, good afternoon, everyone. My name is Adam, and thank you for coming to this talk, in which we are going to talk about manual memory management in .NET. What we are going to do today is actually we'll see how to optimize .NET platform and how to take control of the memory management in order to first work around some type safety mechanism in .NET to improve the performance of our applications. What we are going to do is we'll basically use some magic with pointers and other types provided to us by .NET and by C# in order to re-implement parts of the features which .NET provides out of the box. And this is because we generally want to answer this very simple question. Typical interview question is, where are stored value types and where are stored reference types in .NET? And the common answer is value types are on the stack and reference types are on the heap. However, during this talk, what we are going to see is that it's not necessarily the case. That it is possible to allocate the reference type on the stack, and it's actually we can do much more. So my name is Adam Furmanek, and before we begin, a few words about me. I was a .NET developer for over 5 years, mostly here in Krakow. Now I work as a Scala and big data guy at Amazon in Seattle, Washington. I also recently released a book called .NET Internals Cookbook. So if you are interested in some low-level details of .NET platform, how those things are implemented under the hood, feel free to take a look at it. I'm also a blogger, so there is my blog at blog.adamfurmanek.pl. If you are interested in the things I'm going to show you today, feel free to take a look and feel free to drop me a line either via email or Twitter, whatever works for you. Okay, let's go. So, what we are going to do during this talk is we'll actually start playing with memory. We'll do this in order to improve the performance and to decrease the memory allocation, and also to sometimes disable GC completely to speed our applications. So in order to do that, we actually need to understand quite a lot about .NET internals, about memory of our applications. So initially, we'll go through the object memory structure. We'll see things which are recognized by C# and .NET, but are, for instance, not recognized by ReSharper. And then we'll also learn something about garbage collector in order to verify if our the tricks or the mechanisms we use work correctly. Finally, we'll start actually with our first demo, which will be allocating object on the stack, but we won't stop there. We'll actually start doing even more tricky things. So we'll, for instance, implement a list which is faster than default list of T in .NET. Then we'll actually go deeply into the allocation mechanism to implement custom memory allocator and see what else we can do with it. Okay, so let's begin. We started with this question, where are stored value types and where are stored reference types in .NET? And the thing is, this is not necessarily specified or defined in the standard. The question we ask seems pretty easy, where is this, where is that? But in fact, .NET does not require anything in this area. Typically reference types are stored on the garbage collected heap and value types are stored on the stack. And we know this is not entirely true, because if a value type is part of reference type, it goes to the heap as well. The same goes for closures or async await things if we capture variables like this. But the question is, can we allocate reference type on the stack? And according to ECMA standard, nothing stops us. There are operating systems which do not have a notion of heap at all. They are only stack-based, and in those places, if we would like to use .NET, we would need to actually either implement the heap on our own by ourselves, or we would need to go with stack allocation all the way down. So if .NET standard does not specify anything how our objects are allocated, maybe the question we ask, hey, where are value types, where are reference types, is incorrect. So probably the question we should ask is, hey, where are stored reference types in .NET framework this, in operating system this, on architecture this and this? But if we start asking questions like this, probably this is the reaction we get, why are we asking those detailed questions? Why? Do we ever need that? But this is academic discussion. Let's actually do something useful and see how to allocate the reference type on the stack. So what we need to do initially, we need to understand how are things allocated in .NET. And typically, when we talk about allocation, what we do is we say that when we do allocate objects like this, we say that this O is an object. This is what we typically say. However, in this talk, we need to be a little more precise. Sorry for that. We need to be a little more precise and actually recognize the difference between reference, between a pointer, and between the object. So what the object is in this line var o equals new object is actually the right side of this equation. So this new object is the object. This is the thing which is actually allocated on the heap or wherever else. What is on the left side, this var o, this is merely a reference, which under the hood is basically more or less a typical pointer. And what is interesting here is that this pointer, when we use it like out of the box, is not super useful for us in .NET or in C# because all the like low-level details of this reference of this pointer, they are hidden from us. We cannot access them directly. However, if we get down or get a little lower into the .NET platform, we can actually start reusing those pointers and changing them significantly. So the object, when we take a look at the object, what is important with the object is actually, it's depicted in this slide as this rectangle in the middle, is that the object only has data. Object does not carry methods with it. Methods are completely separate from the objects. Objects are basically like a bag of data, bag of pieces of information which we use, which they carry with them. However, we know there is a reflection in .NET and in C# generally, so we can always ask, hey object, tell me who you are, tell me what you are. And this is what is actually achieved using the so-called method handle or type handle or generally EE class. There are multiple names representing the same concept. Each object carries with it so-called like some kind of a tag, some kind of information telling that, hey, I'm instance of this type. And in this slide, it's depicted as RTTI address. And we can see that this is actually another pointer pointing to this thing on the right, which is basically a method table with all the details of the objects. So all the details of like methods, fields, properties, like inheritance hierarchy, implemented interfaces, everything is there. So in the runtime, during runtime execution, we can ask every single object, hey, tell me who you are, and we can then traverse this hierarchy using reflection, and this is what is happening under the hood. And there is one more thing with every single object, and it's called sync block address. This thing is used, for instance, for locking the objects. So if we want to take lock on the object and store the monitor somewhere, it's actually stored there in this sync block address. Also, this thing stores like pre-calculated hash code. This can also, if we don't have enough space, this can be a pointer to a bigger structure explaining what is actually happening with the object. An important or interesting thing to note here is that the managed pointer, this O, which we have on our, like on the slide on the left side, is actually pointing to this RTTI. It's not pointing to the beginning of the object. It's pointing to this method table pointer. And the sync block address conceptually and physically is stored before this RTTI. This is because it improves performance just a bit. This is basically the similar solution which is used in Java, so this is not something .NET specific. However, when we will be working with the objects, we always need to remember that, hey, there is this sync block which is effectively before the object. So this is how objects are stored in .NET Platform. And now comes the thing. In our first demo, we'll try to allocate object on the stack. How can we do this? So in first demo, we'll cheat just a bit. So we'll just copy existing object from the heap to the stack. In next demos, we'll actually allocate them directly as expected. And first demo, we'll just copy them. And in order to copy them, we need to get our hands on like the raw bytes representing the object data. And I mentioned there is a keyword which is not recognized by ReSharper, and it's this, __makeref. And if we take a look into the documentation, what this thing is about, actually, this keyword returns as the typed reference. It's actually a reference, so yet another pointer, which remembers its type and points to the reference, not to the object, but to the reference. And also there is another keyword, which is called refValue, which does the opposite. It gets the typed reference and returns as a normal reference pointing to the object. So those two keywords we are going to use to actually do this trickery. So imagine that we allocate some object, which is depicted here as this new object on the left with value 65. And this is stored somewhere on the heap or wherever else in the memory. So what we are going to do next is, if this is our new object here, our reference or our pointer, we typically call it like, we can call it object O here, and this is actually the pointer pointing to the object. So what we have here is that our object with value 65 is stored at the address, let's say 5000 here, and our pointer, the reference, has value 5000, which points exactly to the address of the object. And this reference can be stored, or actually must be stored, somewhere else, here as 6000. This is the address of the reference. Then what we can do is we can use the keyword which I just showed you, which is called makeref, and this thing returns us a pointer pointing to the pointer, pointing to the object. So we basically have a pointer to the normal C# reference, and here this pointer is depicted with value 6000 and stored at address 7000. Now, because when we have this pointer, it's not yet super useful for us because it holds the type of the object which it's like is indirectly pointing to. So what we need to do is we need to basically get a normal pointer which will allow us to read the raw bytes or raw data of the object. So we basically do the reference, this typed reference, and what we get here is a pointer to the pointer to the pointer to the object. So when we go with this trickery, we actually can traverse the chain of pointers and finally start reading the object. So this is the idea which we are going to use to start reading and writing objects directly, and then we'll see what else we can do with this approach. And before we actually start doing that, there are a few more things we would like to remember, because like if we start allocating objects on the stack or anywhere else in the memory, we would like to make sure that we are doing the right thing, that it works. So somehow we need to verify this. During these demos, we'll be using debugger, so we'll be taking a look at like raw memory bytes and raw machine code, all those things. However, there is a very simple trick which we can use to see where the object is stored. And if we know how garbage collector works in .NET, we know that the typical implementation, the default one, is the generational garbage collector. So it has three generations, generation 0, 1, and 2. And we know there is large object heap, which stores objects which are at least 85,000 bytes long, or an array of doubles of 1000 values at least. And this large object heap is stored in generation 2. Now the question is, if we copy this object or allocate the object on the stack, in which generation is it going to be? So this is the question. I just leave it for here for a few seconds, and let's carry on and allocate the object on the stack. So let's see our first demo. So what we are going to do is, let me just start this application. What we are going to do is we do have this class Poco, which we'll be using to actually play with the memory and do all the fancy things we want to do. So it has just one integer field. It has method which is non-virtual, so there is no like dynamic dispatch or polymorphism supported by this method. There is virtual method which is actually overridden to string. There is a destructor in case we need it, and this is what we want to allocate on the stack, like ultimately. So what we do initially is, as I mentioned in first demo, we just copy the object. So we create a new instance of this Poco. So our object is this part. What we have on the left side is just a reference pointing to the object, and we create another reference pointing to exactly the same object. So now we have two references pointing to the object where integer field is stored in the initialized to value 5. So then what we are going to do is, because we'll be playing with pointers, we need to actually enter the unsafe block, and we want to allocate some memory on the stack, which we will later use to allocate the object. So what we are doing is we allocate like 10 integers, and we initialize them to value bad food. Why this value? Because it's easily readable, so we want to see it in debugger that we are looking at the correct place in the memory. Then what we are doing is we create the typed reference pointing to the object, and ultimately we do this in direction and traverse the chain I told you. So we get the pointer to the typed reference, we cast it as pointer to integers, we then dereference it, we subtract 4 because we need to move back one integer to get the sync block, etc., to finally get the address of our Poco instance. So let's start this. And this application is now waiting in this console read line. It printed some value like address of E method with value db4, and let's see what we are doing and what we can see under the hood. So what I'm going to do is I'm going to run a WinDBG, and this is raise your hand if you know what WinDBG is. Okay, I can see a few hands in the air. So I'll explain briefly what this thing does. So generally, whenever we want to run or debug the application, we need to have some kind of a debugger. And we typically use Visual Studio to debug our applications. However, what Visual Studio does is just an UI on top of the debugging engine, which is included with operating system. You don't need to have Visual Studio to debug anything. There is a debugging engine directly in the kernel of Windows. So what we need to do in order to use this engine, we basically need to have some UI or some console interface or whatever else. Visual Studio is one of them. WinDBG, the application I'm showing you here, is another UI for debugging engine, and the difference is that WinDBG is supposed to first be used as a standalone application, so we just copy the exe file to production server or wherever else we want to use it. We don't need to install like gigabytes of data to have Visual Studio. And second, WinDBG supports a lot of different plugins. One of them is called SOS, which is Son of Strike, and this plugin is provided by Dotnet platform to actually debug the internal metadata and the raw machine data of our applications. So what I'm going to do is I want to load this plugin. So I'm doing the command load by source CLR. So it tells, hey, load me this SOS plugin matching the CLR version I have here. Now I'm going to do some magical commands like switch to thread number 0. And what I want to do is I want to dump the stack of the application which I'm currently executing. So if we go back to the code, you can see I am in this console read line number 73, and I am waiting here. And if I go to my debugger, we probably can see here that it is in practice in the make ref, and then it's waiting in system console read line. So this is the stack frame of where we are now. Interesting things here we would like to see is that we do have two references, one called hip.poco, the other one called original poco, and both of them point to the same address, this address ending with 838. So both of the references point to the same object. What we also would like to see here is if I now dump the stack frame, which I am using of my current function, what you can see here is, hey, there is this bad food thing which where we allocated 10 integers. So this is the memory we are effectively using under the hood. So this is the place which we are currently executing in. Okay, so let's carry on. And one more thing, I told you that this application prints out something like db4, and if we now try, for instance, dumping this object, so if we dump this object here, what we can see here is first, there is a field with value 5, and also there is a method table with value ending with db4. So it seems that we indeed are looking at exactly the same bytes of the memory as our debugger indicates. Okay, so let's carry on. So I'm resuming the application here, and I am pressing enter here to carry on. So we now passed this console read line. What we are now doing is we already have the object, we have the pointer pointing to the object. What we would like to do now is we want to copy this object to the stack. That's the goal. So what we are doing is we are using this poco address, or actually dereferencing it here, getting the values, and we are assigning those values to the array which we allocated here. So here we should modify first 3 integers of this array, effectively copying the whole object to the new place. So now we printed out the rewritten values and we are waiting in read line. So our application is still waiting here. And if I now, let me just do the break here. And if I now dump the stack frame again, you can see, oh, sorry, I need to switch the thread again. We can see that when I dump this frame right now, what we do have, if I dump the raw memory of this stack frame, we can see that, hey, previously we had 10 bad food integers. Now first 3 integers are effectively modified, and here we just copied the object. So now those 3 integers, they do represent a newly created object which is allocated on the stack. The only missing thing we need to do now is we need to get a reference to this object, and if we can get a normal reference recognized by C#, we can actually do all the magic as usual. So I continue my application, I press enter here. What we are now doing is I am getting the address of the second integer from my array, integer with index 1, and this is the type handle, and I'm creating or storing this address using typed reference into the original reference pointing to the object. So I'm getting the original reference pointing somewhere, and now I'm redirecting it to the stack. I could actually do the same things by like using ref value, or I could just utilize the value which I already have. So let's now break into this application again. Let's switch the thread again, let's dump the stack, and the thing we see now is that this original Poco is still pointing to the previous value, but heap Poco has changed. And it's pointing to somewhere else, and if you can see, this is 0x33, which is like pretty close to the stack frame we were dumping before. So it points somewhere in the stack, and in fact it's pointing exactly where we want it to be pointing. So let's now resume this application and see what we can do else with this application. So what I'm doing now is I created this object on the stack. I want to verify if it works correctly. So first thing I want to do is I want to call methods which are like non-virtual to see if I can call methods. And this write field method, what it does is basically it prints out the integer value. So we are calling this method on the same objects, like different instances, but with the same data. So we should see exactly the same value, meaning value 5 printed out twice. And this is what we actually can see here. So we have 5 from the stack, 5 from the heap. What we are doing next is we modify those values both on the stack and on the heap. We print them out again, and we can see that those two values were modified. And even more, because this object is stored in this array of integers which we pre-allocated on the stack initially, what we can do is we can modify the field of the object using the array which is already there. So we are taking the third integer from the array, because first integer was sync block, second integer is method handle, third integer is the first field of the object. So we get the first field, we modify it with 333, and we can see that, hey, we printed out those values. So we do modify the object and it works correctly. What we can also see is that we can call virtual methods. So we do have original Poco toString, which is virtual, and you can see that it works correctly because this toString just returns the integer value. This is how we implemented it. So polymorphic dispatch works as well. We can also get type to see if reflection works as expected, and yes, this is makeRefPoco as well. And also what we can do is we can check the generation. So I asked you in which generation is the stack, and the answer is for the stack the value printed out is 2. So what is happening here is the generation is basically based on pointers. What .NET does under the hood, it checks whether, hey, is this object in generation 0 by comparing the address of this object to lower and upper bound of generation 0. If it's not there, we check if it's in generation 1. If it's not in generation 1, well, where else can it be? It must be in generation 2. So .NET does not explicitly tells us that, hey, stack is in generation 2. It only tells us that stack is not generation 0 nor in generation 1. So this is like a side effect we should never rely on probably. However, this shows us how this allocation mechanism works in general. Also, because we copied the sync block, we can check whether the locking works correctly. So what I'm doing is I'm trying to lock the stack Poco twice with some sleep for 2 seconds in between. I can run those things, and generally it works as expected. The object is locked correctly. Ultimately, what we may want to do is register this object for finalization, so meaning for the destructor to be called, but this is generally not a good idea because this object is on the stack, so whenever we leave this method, we should never touch those bytes anymore. So this is generally end of demo number 1, and now raise your hand if you do believe me that I copied the object to the stack. I can see some hands. This is a success. Okay, so that was pretty easy. Let's actually see what else we can do. Let me just stop the debugger here. Let's close it. Let's close it. And actually, what we would like to do now is we would like to implement the unsafe list. How does list of T work in .NET? So generally list of T uses the references. So what it stores is just a pointer to all the objects. When we call add, it stores only the references. So like 4 or 8 bytes depending on the architecture. So in C++ terminology, this would be probably something like vector of shared pointer or whatever else pointer is now fancy in C++. And if we traverse the list, we do basically the ping pong style. So we go to pointer object, pointer object, pointer object. What else can we do? Well, instead of storing references to the objects, why not store the objects itself? So let's go with implementation, which whenever we call add on the list, we take the whole object, copy it to the list, so then when we'll be traversing the list, we can just linearly go through the memory. Now, working hypothesis is that this should be much faster because we do have caches, L0, L1, L2, so when we read objects, we don't need to do the ping pong, so this should be faster. And let's see if this is in practice what is happening. So let's go to the demo number 2. And let's implement the unsafe list. Let me just set my project as a startup one. Let's start this in the background. And I am running this in virtual machine, so results may be generally skewed, but they typically show exactly the pattern I want you to show. So while this will be running in the background, I will show you the code. So we do have some POCO with 16 integers just to have some memory, because like there are actually 2 working hypotheses. First, walking through the list should be much faster because we are linearly scanning all the integers, but adding objects to the list should be slower because instead of copying 1 integer, we need to copy like here would be 16 integers plus sync block plus method handle. So generally many more bytes just to add the object to unsafe list. So let's see if values match with our theory. So what I'm doing is I do have 3 methods. I test 3 collections. I test array, I test list of t, and I test unsafe list. So what I do is I do have a helper method initializing me some object with like deterministic but different values every time. So I know that in practice, this application works. It's not a coincidence that that there is some optimization, clearing the objects or whatever else. So first test is test the arrays. I pass the elements count, and I start my stopwatch. And what I'm doing is I just create a new array with given size, and I create the POCOs and put them in the array. I stop my stopwatch, bring the insertion time. What I do next, I restart the stopwatch. I walk through all the elements. I sum all the fields. I print out the sum and the calculation time. I do exactly the same for list of t. I do pre-allocate the list of t in order to avoid the reallocating it in the middle. And apart from that, everything is the same. Creating objects, adding to the list, restarting timer, summing things, printing out. And then I do create my unsafe list. And in my unsafe list, I specify the type, I specify the object size. Apart from that, everything is the same. So what I'm doing in my benchmark, I run it 3 times for each of the collections, and each collection will store 20 million elements. That's what we are going to do. Obviously, this is not a benchmark per se. This is just showing you the rough idea. I do have a benchmark with benchmark.net application, so if you are interested in it, take a look at my blog. And now let's see what unsafe list does. So what we are doing is we are basically allocating a big array of integers, and we do some bookkeeping, like how many objects we have, etc., etc. We store the element size and all those things, and when we call add, we just advance the pointer, the index to the next element. We do the magic with typed references. We store the objects, etc., etc. We can pre-calculate the reference to the object, or we can just calculate it on the fly, because whenever we want to access the object, we need to get a reference pointing to some object inside the list. So what we are doing is we are basically taking our reference and we just return a result. Because this is just an pointer, this is just one integer we need to give to our caller pointing to the object in our list. So let's see what we do have here. So let's make this a slightly bigger, and let's see if results are as expected. So generally adding to array, this is something like between 8 to 18 seconds here. For list is between 5 to 16. Because I'm presenting here, my computer is obviously a little slower than typically. Generally, this is something like 6 to 7 seconds with my machine typically. However, with unsafe list, insertion time is constantly below 3 seconds. So we can see that adding objects to the list is much, much faster than adding to normal array and normal list of t. When it comes to traversal, here we can presume that traversing is slightly slower. In practice, it's generally the same when we run this with benchmark.net. So the takeaway from this demo is that our working hypothesis for scanning the objects didn't work. Scanning the objects is if the same or slightly slower when it comes to unsafe list. However, adding objects to unsafe list is much faster than adding objects to normal list of t. Why is that? Well, I will leave you this because this is a lot of optimizations going under the hood. So I won't explain all those things into the detail, but generally, try remembering that we can implement these things a little bit better. And if you are interested in how it works under the hood, this is like a machine code generated there. So feel free to download the slide deck after this talk and examine what is the difference. Okay. So that was demo number 2. In demo number 1, what we did is we copied the object from the heap to the stack. In demo number 2, we copied the object from somewhere, from the heap, to our unsafe list. What we actually did, but we did not explain this explicitly, is that we can copy the object or write the object anywhere in our memory. It doesn't need to be on the stack, on the heap. It could be anywhere in theory. Like, it's hard to imagine where else it could be. But generally, we can implement generic allocator, which will allocate objects anywhere we like. So let's move on to demo number 3. And let's see how we could implement such an allocator to have allocation, to take control of the allocation. So let's set a startup project here. Let's run this application. So what I'm doing here is I do have allocator demo. I do have some like structure, enum, classes, everything else, just to show that it works with all the possible types. And then what I'm doing is I am basically implementing allocator in this way that I provide a lambda explaining how to allocate, how to construct the object. We don't want to construct the object anymore. We don't want to copy it from here to there, but we want to have the compiler support. We want to have some support telling us that, hey, this object will be created correctly, initialized as expected, all the types match and all those things. So what we do is we provide a lambda of type expression of func returning the object, and this lambda just uses one new instruction to create the object, and we have all those things, and we pass this lambda to our allocator alloc method. And how this allocator works? Well, this is basically the same thing you probably did while you're operating system courses or whatever else. So you can come up with any allocation strategies and test all of them in C#. So here I am just using free chunks and occupied chunks approach. So I do the first feed basing on the object size. So I do have my chunks. I store my free chunks, occupied chunks. What I'm doing is when I call allocate, I get the object size. I get first free chunk. I try allocating object over there. I allocate it. I clean the finalizer in order to stop GC from messing with the object. I do bookkeeping, remove free chunks, etc., etc. Now the thing is, how do I call the constructor? And this is actually pretty simple because we actually have two approaches to invoking the constructor. First approach is we can get the reflection and call the constructor on the allocated object. You can call constructor multiple times, even for already allocated and constructed objects. The other approach we could do is just generate some IL code doing this magic. So we do create the dynamic method. We just load the pointer. We just go through all the parameters in order to evaluate them, to put them on the stack correctly, and then we just call the constructor. So this is effectively what this calling constructor, how it works under the hood. We just recreated here, and as we can see that, hey, the object was created correctly. All the values are here with enums, structures, classes, boxed types, unboxed types, anything else. So this is how we can control the allocation, and with this approach, we can allocate objects anywhere we like. So this is neat, and it generally works. However, we don't like this approach because what we are doing is we are re-implementing the whole part of .NET. Like, we already have new object, it works. Why bothering with creating all those things, calling constructors, etc.? The question is, can we somehow ask .NET, hey, instead of me doing all the magic, allocating memory, calling constructor, can't you just call the constructor and prepare the object correctly for me, but in the place I specify? So basically, can we somehow hijack the new operator in .NET to allocate the memory in the place we decide? And this is then our next demo, which we'll actually do. And what I want to show you in this demo is that if we can access raw memory bytes in our application, and we can do this with pointers, then we can actually do anything you can imagine. So let's see how to hijack operator new in .NET. So what I'm going to do first is I just close all those things. And what I'm going to do is I will start generic unsafe alloc project, start it. And what we are doing here is I am creating my allocator, the one which I just showed you how to implement, and I am allocating some object using this allocator. Because I am allocating this directly, I want to show you that this object is in generation 2. Then I allocate normal object using new operator. This should be in generation 0 because this is normal typical allocation. Then I hijack my new operator, I allocate new object, and I print out the summary. So here you can see that my hijacking is commented out. So what we are seeing here is that allocator is in generation 0 because this was normal allocation. Object allocated by allocator is in generation 2 as shown here. And then those two new objects here are both in generation 0 because nothing has changed. So let's close this. Let's uncomment this line. Let's start the application again. And let's see if there is any difference under the hood. So let's just recompile this up, wait for it a few seconds, and when it pops up on the screen, we should see that after hijacking this new operator here, we should be seeing the object in completely new place. Now the thing is, my application doesn't want to start, but it's building under the hood. It only takes like lots of time, so let's just wait for it. There it goes. Okay, so it's still waiting in this console read line. Let's press enter, and now you can see that the last object which we allocated, new object, is now allocated in generation 2, presumably using our own allocator. Let's now see how we can do this, and I will do this twice. First, I will do this manually to show you the idea, and second time I will do it automatically, or I will show you how to do it automatically. So let's now recompile this application. It's waiting in this console read line, and let's start WinDBG application again attached to the process, and let's see what is happening under the hood. Okay, so here we are. Here we are. Let me make this bigger. Again, load by SOS CLR to have the plugin for doing the magic. I'll just go with a short cheat sheet here to not type all the commands. What I'm trying to do here is I want to show you what is happening under the hood in the method which we are executing. So when I dump the address of the method which is here, what we would like to see is how this thing is executed, what this new something does under the hood. So let's wait for it a few seconds, because during presentation it always takes time to download some symbols, even though I'm offline. But when it finishes, we should see the machine code, or actually I should have the machine code at the same time here. So if we dump the code of this method, what we can actually see here is whenever we call the new generic memory allocator, second line on the screen shows us that it's calling some core.info help news fast method. And this is method provided by Dotnet, actually doing the allocation and getting the memory for our objects. Then next 3 lines, they do bookkeeping to store the reference, and then the call something is actually calling the constructor. So let's now see how this call core.info help new fast, how does it work under the hood. And if we decompile that method, what we see here, this is the normal bump the pointer allocation approach. So what Dotnet does is it's doing the same things which we were doing in the previous demo. So first it gets the size of the object to allocate, then it gets how much of the memory is already allocated, it adds the object size to the pointer to see if we still have like free space in the array we are using, and then if it does not, then we need to go to the operating system and say, hey, give me some more memory. So we do this jump, but if we don't do this jump, what we are doing, those 3 lines, move sub mov, they basically do the bookkeeping, they calculate the object address, and they return the pointer to the object. So this is what is happening under the hood. Let's see if this decompiled those things. It did. So now a line here should be like 167. So you can see this is the thing. So we are calling this core.info helps new fast, and this is the method which we are actually using. So let's take some notes and let's store this address as .NET allocator. And if we now dump this address, this method, what we should see is, yes, this is the bump the pointer things with write barriers, all those things. Okay, so what we now want to do is, I do have memory in my application which is actually called raw allocate, and which is doing the same thing as the normal allocation method in .NET. It gets one pointer pointing to the type of the object which we need to allocate, and it returns one pointer here. This method is also static. If it wasn't static, it would have yet another parameter passed to it, which would be the pointer to the instance of this of the instance of the object on which we call the method. But since this is static, it doesn't have this additional parameter, so it matches the calling convention perfectly. So what now I can do here is, assuming we can use this another cheat sheet, to basically get the address of this method, and if we start dumping it, we can see addresses like program CS line 89, and 89 should be somewhere like here. So we are looking at the correct code. So this is now the address of our allocator method. So what we can do now is we can cheat .NET a bit. Let's take this original address, let's modify it, and as a first instruction, let's put a jump to our method. So I'm putting the jump here, and if I'm done correctly here, I should be able to dump the original .NET allocator method. Again, I should dump it like here, and we can see there is some jump initially. If I now start the application, assuming I didn't mess up any of the pointers right now, I should press enter, and you can see that even though my hijack new is commented out, when we take a look at this application, we can see that the object was allocated in generation 2. So it went through our allocator and did all the magic. And to convince you, I will now stop the debugger even more, and to convince you that we can do this automatically, I will actually recompile this hijacking again. I will restart my application, and what I'm going to do now, I will attach to the process with my Visual Studio. So I'm attaching here. Now what I want to do is, I want to put two breakpoints here, and I want to press enter to go through console read line, and also I want to put a breakpoint here. Assuming that we did not hijack new, if I now press continue, what should happen? We should just go one line further to this console write line. But because we did hijack new, when I hit continue, we end up in raw allocate. So we can see that we are going through this method. I can hit continue again. Now we are in this console write line, and if I hit continue again, we can actually see that we end up in this method once again. Why is that? It's because when we go through the string allocation here, what I'm doing here is I am basically concatenating some strings. So this allocates the memory. If I hit continue once again, you can see there is yet another object being allocated under the hood, and there is some external code marker showing us that, hey, we are entering like the low-level stuffs of .NET to do some printing out, and we go through the allocation mechanism again. So generally this shows that yes, this raw allocate is used not only for our objects, but also throughout the whole .NET implementation currently. So in general, it works as we want it to work, to take control of the new allocation mechanism. Okay, and now comes the last thing. Like, okay, we did some allocation, we did some magic, we actually moved objects here and there. The question is, can we do something else? And the last demo which I'm going to show you today is how to improve GC performance in .NET, again, using some low-level optimizations. So let's kill the old applications, let's go to no GC ref, let's mark it as a startup project. So what I'm doing here is, let's start it in the background. This is yet another benchmark. What we are doing is we are creating a big graph of object. This is a binary tree. So we want to allocate something like a gigabyte of memory. Even if we allocate it using our allocator, there is still one more thing in .NET which doesn't allow us to take the full performance or improve the performance even better. It's called garbage collector. Whenever I call GC collect, GC will try traversing this object even though it was allocated by us, and GC had nothing to do with this object and didn't even know that it's allocating the object. So what I'm doing here, I'm creating this big graph. I am allocating with it with some like depth 25. This should give us like a gigabyte of the memory, and then 10 times I call GC collect, wait for it to complete, etc., etc. I wait for all the finalizers, and I just print out the timestamp, how long it took. So if we take a look at here, we can see that, hey, whole allocation took, whole cleaning for 10 times took something like 30 seconds, and we can see here that, yeah, on average it took 2-3 seconds to release those objects, even though nothing changed and those objects were not allocated by GC or by .NET mechanisms. Can we do better? We can do better by doing different object graphs. So let me replace this. Let's run this again. And in the meantime, let's see what I'm doing. Previously, our graph was basically, we did have a normal object and two children, left and right, using big graph references. Yes, typical implementation. What we now want to do is we want to hide those objects from .NET GC. How are we going to do this? Well, obviously, we replace strongly typed children with just integers, with just pointers. So we allocate them somewhere using unsafe list. I'm using unsafe list implementation again. And then when I add objects, I just get a normal integer, normal pointer value. So now when we call GC collect, even if some reference pointing either to the root of this graph or somewhere in the middle was stored somewhere in the middle, like in the meantime in register, on the stack, wherever else, GC will start entering and traversing this object, but it will stop after seeing like one instance of this because it cannot get to the children because it does not recognize them as strong types. So if we now take a look at the performance of this application, it's less than like a millisecond here, or actually close to 3 milliseconds. So much better than 30 seconds, which we had before. So generally here we took not only the control of the allocation, where we store the objects and how we store them, but also we have hidden them from the GC, so garbage collector cannot traverse them, and we get some performance benefits. Okay. This is it when it comes to demos. This QR code points to the slide deck, or actually to my series where I explore manual memory management even more, etc., etc. So feel free to download the slide deck and read the code if you're interested in. And now comes time for questions. Okay, there is one. The question is, why do I have all my examples in virtual machine? That's actually something not related to .NET at all. It's just I don't use this laptop with all my presentations. Sometimes I travel with different machines. So just to make it easy, I just copy the machine. So I don't need to care. Because those demos are slightly lower level, there are differences between like x86, x64. Virtual machine takes care of that. So it's just simplicity. Any other questions? Okay. If there are no more questions, let's quickly wrap up with some references. So if you are interested in details of .NET Platform, there are a few books you may be interested in. So generally, like you can start with Jeffrey Richter's CLR via C# and then going down and down to even lower levels of the like .NET, C# or operating system, etc., etc. If you are interested in things like architectures or how those things work under the hood, I highly recommend taking a look at the blog by Raymond Chen, the blog called The Old New Thing. The author of this blog examines a lot of different architectures and other like low-level debugging scenarios similar to what I showed you today. If you are interested in things I showed you explicitly, like allocation on the stack and all those things, links pointing to my blog showing you how to do this. If you are interested in similar things but outside of my blog, feel free to take a look at these links, pointing you to similar implementations in .NET, in Java, or details of the object allocation somewhere else. And having said all of that, it's time to call it a day. So my name is Adam Furmanek. I'd like to thank you for attending this talk. I hope you enjoyed it. Thank you.